All right, so now we move on to lesson 15, which is forces along the inclined planes. This is an extension to lesson 13 and 14, where we talked about net forces in the horizontal planes. We talked about net forces in the vertical plane. Now, what we can kind of do is interweave them a little bit in terms of dealing with them on the inclined planes and see how those two forces can come together. Now, they're not going to be perfectly synchronous with one another in terms of we're not going to take the 13 and 14 material and directly put them together. But what we're going to do is use the concepts from those ideas of we've now talked about horizontal independently, vertically independently. How do those two ideas kind of mesh to make some sort of overall combined problem? Now, lesson 15, forces along inclined planes. We want to go into the introduction here and introduce a specific circumstance which kind of gets us thinking about how objects accelerate on inclines. So, first and foremost, we have some sort of mass that is sliding down a frictionless incline that makes an angle of elevation of 30 degrees with the horizontal. Another mass is dropped off the back of this incline or just off to the side, and we want to figure out what is the acceleration of both of these masses. So we got situation one, situation two, where this one is one, this one is two. Now, let's start off with first and foremost the object being dropped off the back. Now, if I know that this object is just being dropped, we would say that this object is experiencing free fall. So I want you to write that in here as that this is a free falling block. And when an object is in free fall, we typically said that the acceleration was negative 9.81 meters per second squared. And that goes all the way back to kinematics, where we said down meaning negative or in the negative direction, 9.81 because it's just something that is close to its surface accelerating towards the surface. Now, if I go over to the object that is experiencing acceleration on the incline, this is a totally different situation. And right away, you should be thinking, there's no way that the acceleration is 9.81 because it's in sort of contact with this surface. So I couldn't boldly claim that it's 9.81. Let's do a little bit of a derivative here and see what maybe this value would be. So right away, I want to say that acceleration is going down the incline in this way. So we can call this the acceleration of the incline, which is that kind of red marker as it's sliding down. Now, this can be broken into the following components. We can break this into the following. If I know that the acceleration on the incline is heading straight down, we can consider there to be some sort of y component. So I'm going to consider that to be the downwards component. And then I'm going to consider there to be another component here. And I'm going to even backpedal this just slightly. I'm going to make this down, put an arrow. I'm going to put this over, put an arrow. Now, if we're talking about this in terms of acceleration, well, the overall acceleration on the incline is a component or is the combination of some sort of acceleration in the y direction and some sort of acceleration in the x direction. So I'm going to call it ax and ay. Now, if I was to solve for the acceleration on the incline, here's how I would do it. We know that this interior degree here is 30 degrees. So this might be a little bit tight, but I'm going to try and fit it within there. This is 30 degrees right here. Now, if that angle in the interior is 30 degrees, off to the side, let's figure out what is the acceleration that this object would experience in terms of the incline. Well, in terms of the y direction, we would assume that this one would be the 9.81. So I'm even going to fill that in below here. If I looked at this, I should say that in the y direction, acceleration is 9.81, and I'm just going to make sure that that's a little bit thicker here, 9.81 meters per second squared. And when I put this together here, I can say that the acceleration of the incline is equal to, well, we have our AY, which is our opposite, over the adjacent. And I should actually put that 30 degrees. I'm just going to go back and correct something here. On the interior of the triangle here, I'm just going to take that 30 degrees out here. The 30 degrees actually needs to be right here. So I'm going to write that 30 degrees here. Now, if the 30 degrees is in this part of the triangle or the low left, like it is on the regular part of the triangle, I guess I should draw the parallel between those two here. We say that our opposite is AY, and I'm going to make sure I'm using the same color here. This is our AY, divided by the hypotenuse, which in this case is going to be our, and I'm going to backpedal this even more here. I'm just going to erase this piece out here, and I want to make sure I derive this according to the sine ratio, because if 30 degrees in the bottom here, we want to get our acceleration of the incline based on that. So we're going to say that we have the following. This will be sine of 30 degrees is equal to the opposite, which is AY, or the y component of acceleration, over the hypotenuse, which is the acceleration of the incline. Now, if this is written like this, I'm going to swap these two here, A incline, sine 30, and I'm going to do the following. A incline is equal to AY divided by sine 30. Now, what this is going to give us is the following. I'm going to get an A incline, which is equal to AY, which is 9.81 meters per second squared, divided by sine 30, There we go. And if I put this into my calculator, 9.81 divided by the sine 30, I'm going to get an acceleration on the incline like this, there we go, is equal to 19.62 meters per second squared. Now, there is a huge issue with this. If I look at these, my free fall acceleration was 9.81. My acceleration on the incline is supposedly 19.62. This seems like a massive problem. Here's the problem with this. And the reason I want you to ignore this derivation is realistically, you wouldn't even have to write this in your notes. If you wanted to, you could, but we want to ignore this derivation because the acceleration on the incline should not be greater than 9.81. So that's what we want to write in the problem here. The acceleration or the acceleration on the incline should not be greater than 9.81. If it is greater than 9.81, we have a huge issue. We need to say that the acceleration on the incline must be less than the acceleration due to free fall, which I'm going to denote as FF. So if I zoom out here, just in the theory or the overall synopsis of this, we would look at this and say, well, free fall should be greater than something that is on an incline. If it's not, there is a huge issue here. Now, here's where we go into the real definitions and the ideas that we're going to follow that make these problems work appropriately in the way they should, according to how the forces interact on this incline. If we go down, first and foremost, we want to call or recall a specific note that we talked about in our lesson 13, or when we dealt with forces on a horizontal plane. Unless the object is purely sitting on a horizontal, we cannot say that our FG is equal to Fn. Meaning, if I look at my diagram here, do we see how that the Fn and the Fg are not on a purely horizontal surface? In fact, these two forces are interacting on some sort of incline, and I can't just say that my Fn here is equal to my FG down here. That would make no sense because not only are they not directly across from one another or directly in line with another, but they also have an FG where it's broken into these components. And so we don't want to say that our FG is equal to Fn because FG has these two components in which one component might equal Fn, but the overall magnitude of FG and Fn are not equal and opposite to each other. So just be very, very careful with that. They are only equal and opposite if the object is sitting on a horizontal plane. Now, here's where we expand our definitions into what we're going to deal with in terms of inclines. First and foremost, if I look at the diagram here, before I highlight some things on the left here, we have an Fn, or a normal force, a contact force that is 90 degrees to the surface. Very critical. Now, here's where we introduce some terminology, F perpendicular and F parallel. What these essentially are is the components of Fg that are the y component and the x component. And so how we're going to analyze this is we're going to say the following. F perpendicular is often written as F with an upside down T, aka F perpendicular. Or what we could do when we're first learning this is write it as FG in the y direction. If you want to write it as FGY, this would be totally fine and I would completely accept this. In terms of F parallel, we write this as F with almost like an 11, aka parallel lines, or we could write this as FGX. And as you're learning this, if you feel more comfortable with the FGY and the FGX, I'm totally fine with that. In fact, those are totally valid. However, when we go forward in the notes, we're going to deal with a lot of these two. So force perpendicular and force parallel, these are the components of the FG in terms of the y and x direction. And we just very commonly use this language. But FGY and FGX are totally acceptable as well. Now, if I want to solve for these, just like we dealt with in kinematics when we broke things into their components, we can break them into the components where we recognize that this is a 90-degree triangle down here. We have some sort of angle, which is here, and that angle can then determine what ratios we use. So for perpendicular, because of its relation to the theta, if theta is here and FG is the hypotenuse, then this must be my adjacent. And so if I'm dealing with the perpendicular, it's going to be the cos ratio, aka F perpendicular is the hypotenuse times the cos ratio. Now, if I look at the force that is represented by F parallel just uses the opposite ratio because if theta is here, this is my opposite, this is my hypotenuse. Thus, the ratio I'm going to multiply it by is hypotenuse times sine theta will give me F parallel. Now, something that's going to be very, very important here to note in both of these, F parallel is the component of FG that causes the object to move down the incline. In comparison, when we talk about FG perpendicular, it is equal and opposite to the normal force. So in your notes, here's what I would recommend. When you draw in these diagrams here, I want you to put a connecting arrow between these two forces, or Fn and F perpendicular, because these are equal forces to one another. They're equal plus opposite. So you could put just equal, you could put equal and opposite. I would be okay with you just saying equal, because we want to analyze these and say, if the object isn't flying away, aka flying away vertically, or it's not crashing through the surface this way, you would say that these are perfectly in balance. And by Newton's first law, there's no sort of vertical movement off of the incline. The box doesn't fly away, it doesn't crash through the surface, it maintains its vertical height on this given horizontal plane. Okay. Now, as we move forward here, something that's very important to realize with the net forces here, or before we go into our given problem set, is when we derive our net force, here's how it's done. We know that these two forces are equal. So again, if you want to make sure you write this in your notes, we have an Fn and an F perpendicular that are equal to one another. And the fact that they are equal by Newton's first law just means that they are maintained. The F net is zero. We don't see any sort of vertical movement off this incline. Something else that is extremely critical for us as we move forward here is the following. Let the down direction, or let down the incline, be positive. And the reason we're going to consider this to be positive is because when we look at the diagrams of these inclines, the box is moving down. And so if we're going to consider the movement going down, whatever the box is in terms of its directional movement, that's going to be positive. So if it's heading down the incline, it's now positive on the way down. And I know that's a bit of a shift from kinematics, because in kinematics, the object was rolling up the incline typically, and then thus we made positive in the up direction. In this case, the box is moving down, so we're going to make that our positive value here. And so we see an index of positive on the bottom, negative on the top. We see all our vector components broken apart, and now we see this new introduction of FF. What I typically do in the notes is I'd like to draw FF up here. So I'll draw FF in the diagram up on the box here. In the notes, they put it down here. So they put it opposite of the F parallel, which, isn't the worst idea. But when I look at this, I always like to draw the forces coming off the box itself rather than drawing them in terms of like off of one of the vectors, which might be a little more confusing. So I would always tend to draw FF on the box if it exists. So we know let down be positive. On these ones, we want to go back to a specific thing here. That is let G be signless. Please use a signless G, because if you start to use negatives and positives on G, it's just going to throw you off. It's just going to confuse you. So what we want to be thinking about in these problems is the force negative or positive, which goes back to our lesson in 13 and 14 when we talked about the idea of, we can either say that G has a sign, or we can just denote the actual force overall is negative and positive. That's the method we're going to use. Use a signless G. Do not put in negative with 9.81. Last note here is the following. To deal with friction, we actually have this nice workaround, which we learned the other day, or we learned in lesson 13, and it was this one here. When we were on the horizontal plane, we had some sort of relationship between vertical forces and horizontal forces. Namely, the force of friction has this connection using this coefficient of friction to the normal force, or the apparent weight that's experienced. Now, that's given to you on your formula sheet, the part in blue here. But what I want to do is connect these two together, because you're probably thinking like, what the heck, how are these two related to one another? I go from mu Fn to mu Fg cos theta. Well, how does that happen? Well, just like off in our diagram here, we know that our Fn, or the normal force, is equal to the perpendicular force. So the missing line we're missing here is the following, and I would highly recommend you put this in your notes. The force of friction is equal to mu F perpendicular. That is very, very important to put in there. That missing piece that connects this all together, because then from there, we know that our F perpendicular can be defined by the hypotenuse of the triangle FG multiplied by the cos of that given degree of whatever it is. And then the mu just stays consistent between all of these, because again, it's a measure of the stickiness of the surface, or a measure of the surface conditions themselves. Okay, this connection is going to be something we deal with a lot. And when we get to a specific example today, I'm going to derive this one more time just so that we can see it all together. And then we're even going to formalize it just a little bit more. Now, what does this mean we have for a net formula based on this diagram? Well, according to this, if I know that my Fn and my F perpendicular are balanced, then my F net can be defined using the following. F net is equal to F parallel, which is the force pulling it down the ramp in terms of G. If you really wanted to, you could write this below as well. You could write it as FGX, or the force due to gravity in the X direction, plus your force of friction, which is resisting the box going down the incline or up the incline, depending on the problem. So, we can't classify up or down in terms of overall systems, but what we can do is say that this would be representative of the net force, where our F parallel is typically the force bringing it down the ramp, our FF is the part that's opposing it, and overall they combine to give us some sort of net force. Now, let's work into the problems here. So right away, we have a 445 Newton box that is sliding down a frictionless 25-degree incline. Find the force that causes the box to slide down the incline. Now, right away, we want to indicate a couple things here. When you see this, just like we did in lesson 14, you need to be aware that this is talking about the weight of the object. And so I highly recommend in your notes, you say that this is the weight of the box, which we know from lesson 14 weight is symbolic of Fg, or the true weight of an object. Force due to gravity causing this thing to be pulled down to the surface of Earth, or whatever planet we're on. But in this case, we're going to assume it's Earth. The other piece they mention here is this: down a frictionless incline. Right away, as soon as you hear those key terminologies, or you read those key terminology pieces, you want to say your FF is equal to 0 newtons. Really, really important. This means that there's no resistive force that's preventing the object from going down the incline. You now just have some sort of FG component that is bringing this down the incline. Now, as we draw these in, we want to always draw a free body diagram. I recommend drawing a fairly decent sized triangle. And we did this in class as well. We want to draw them decently large because of the amount of forces that are applied here and the complexity within the actual free body diagram. You don't want to be short for space. Now, here's what we have for forces. First and foremost, we have an FG that pulls the object down the ramp. We have some sort of FN, or a normal force, that is a contact force due to the surface. We do not have a frictional force, so I don't want to put some sort of arrow going in the backwards direction. What I'm going to do is just make sure we indicate these. So this is my Fn, or the normal force. This hypotenuse value is my Fg. And now we want to break this into the components. We're going to have one that is a y component of Fg, one that is an x component of Fg. Now, for this specific example, because we're just learning it now, what I'm going to do is write this in as this is F parallel, or perpendicular, I should say. Perpendicular because it forms a 90 degree to the given horizontal. So I call it F perpendicular, or what we can call it as FGY. The other force that I have here is F parallel. And you're probably thinking, why is it called parallel? Because this component is parallel to the horizontal surface it's on. Now, this could also be classified as FGX. So we just got to be making sure that we're being careful with this and making sure we're including the detail there. Now, they also included that this is a 25-degree incline. So what I'm going to do is right in the triangle here, we're going to put 25 here. We're also going to put 25 within the triangle. Now, there is a specific proof, or there is a specific connection of why the 25 in the low left is equal to the 25 in the triangle. It deals with the symmetry of these triangles and the overall math behind the connection between their lengths and the ratios between them. But we're not in a proof-based course, so I don't really care to go too much into that. What I want you to do is just identify the fact that the degree in the bottom left of this triangle is equal to the triangle that breaks apart our FG component, and then maybe I'll provide some supplemental material around that. But I would rather you mastered the actual forces and the connection between the forces than trying to memorize why a degree, or even derive why degrees are equal within these two triangles. Now, we're not quite done our free body diagram yet. The one thing we're missing here is the signs representing positive and negative direction. So what I recommend is you put your index. We know the box is sliding down the incline, so I'm going to put positive down. Negative is going to be in the upwards direction, or up the incline. And what we're going to want to figure out here is, let's put together our FNet statement, or now that we have our free body diagram, put together an FNet statement. From there, what we can do is figure out the force that we're looking for. So, because they say they want the force that causes this to slide down the incline, therefore, let's write it out. Our FNet is equal to F parallel plus FF, and I'm going to make sure to put all my signs on here. There we go. Now, they told us that this was a frictionless environment, or a frictionless incline, so I'm going to put 0 newtons here, leaving me with the following. We know that our FNet is going to be equal to F parallel, which by definition, let's put this together. If 25 degrees is here, F parallel is the opposite. The hypotenuse is FG, so we're going to use the sine ratio. This is going to be FG sine theta. Excellent. There we go. Now, realistically, what we could do is we could look at this FG and make it into MG, but what they actually gave us originally was the FG. So we don't need to do any sort of special conversion. What I'm going to do is write this out as FG, which is 445 newtons, multiplied by the sine of the degree, which in this case is 25 degrees. And this is going to give me an F net value, or the net force that's causing this to go down the incline, which is equal to positive 188 newtons. Now, you could also answer this as the following. You could say this is 188 newtons down the incline if you really wanted to, which I'm just going to short form as down the incline like this. There we go. So either one of these answers would be totally acceptable. Now, again, what is the actual force? Like, I know we said that the F net, or the overall resulting force that causes it to go down the incline, is 188, but the connection we just built is that if there's no sort of friction, the only force that causes this to go down the incline is the F parallel, or the component of gravity in the X direction. That's the large connection I need you to make here. All right, let's go on to example 2 here. Example 2, we have some sort of 44.3 kilogram box sliding down a 40-degree incline. If the acceleration on the box is 0.250 meters per second squared down the incline, what is the force of friction? Okay, very similar setup here. The only thing we have that's different here is the force of friction, and we're solving for a slightly different variable, aka the force of friction, rather than the overall force bringing it down the incline. Now, what we want to do is right away, we want to draw out our big triangle so that we can put in our free body diagram. So I'm going to put together the triangle here where, again, it's sliding down the incline. So I'm going to make sure I put the box right at the very top. Let's start by putting in some forces here. So I know I have my Fn, which is going in the upwards direction. I have some sort of overall Fg heading down. And so I'm going to write this as, there's my Fn. Here is my Fg, or my force due to gravity in the downwards direction. I want to break my FG into the components because it's on an incline and it's not just directly in the vertical plane. Now, in this example, what I'm going to do is I'm just going to purely put F perpendicular and F parallel. And hopefully that's okay for you, because realistically, again, you could put FGX and FGY, but for now, I'm just going to start by putting in F perpendicular and F parallel. Now, the other thing we need to put here is our index and the degree. So what I'm going to do is put the index first, where negative is up, positive is down. The other thing we need to put on this diagram is the degree angle. In this case, we had a 40.0 degree angle. And so I'm going to make sure I put that within the triangle and on the outside there. There we go. And again, we could derive that, but I don't want to focus too much on that. I want to focus on how these things come together and how the forces are related. Now, there's one more force in the diagram that I almost overlooked, and it was this one here, our force due to friction. Again, you could, so just being realistic with this, you could put force of friction down here. So I'll even put a dotted line representing the other optional place to put the force of friction. If you wanted to put it down below where the F parallel is to show that it's opposite of that force, that would be totally fine. However, I generally prefer this method here. Now, in the end, what we're going to solve for is the magnitude of this force of friction. That's what we're looking for. So let's put this all together in terms of an F net statement. Now that we have our free body diagram, the F net is equal to, from our previous page, our derivative of this, we said F parallel plus force of friction was equal to the F net, because we know that our Fn and our F perpendicular balance out with each other, or they're equal and opposite, so the object isn't flying off the surface and it's not crashing through the surface. Now, what we're going to do is we're going to isolate for FF here. To isolate for FF, we're going to say FF, or the force of friction, is equal to the F net minus F parallel. Okay, perfect. Now we're going to expand this out a little bit. So our F net will be equal to mass times acceleration minus our F parallel. Well, this is going to be in the opposite over hypotenuse position. So again, we're going to use the sine ratio. This is going to be FG sine theta. Now, I'm not happy with leaving this as FG. So what I want to do is, instead of writing FG, I'm going to write FF is equal to mass times the acceleration down the incline minus mg sine theta. Now, what I need to do is realize I could just plug in the numbers here, or we could use a Math 20-1/10C concept. Force of friction is equal to our greatest common factor is mass. And so I'm going to take it out of the brackets and leave acceleration minus g sine theta. Okay, now this is where we put all together the problem here, and we need to be very, very careful, because originally you would think, oh, okay, well, my mass in this case is 44.3, so I would agree with that, and this is going to be in kilograms, multiplied by my acceleration, which is 0.250 meters per second squared. We're all good here. What we don't want to do, though, is put a sign for g. So this is going to be just positive 9.81 meters per second squared, and I'm not going to put any sort of sign with this. I'm not going to, like, the sign here is operational. Operational sign, operational sign, operational sign. That minus had nothing to do with being a sign. So we just put 9.81 for G. And then in terms of this, I'm going to hope I have enough room here. We're going to put in sine of 40 degrees here. There we go. Close the bracket. And I just want to double check that's 40 degrees, which it is. Great. Now, therefore, we get a force of friction equal to, now from our magnitudes here, we should find that it is negative 26 or 268 newtons, which we could also say is or 268 newtons up the incline. So I'll just short form it as up the incline like that, just like I did in the previous problem. So either answer would be totally acceptable. Negative, why? Because it's going against the motion. Our force of friction is against the positive direction, which is down, so it should be negative. Now, that piece here, even if your calculation ends up being positive, you should always recognize that you will have something that it should be negative. In this case, though, it should be a negative when you do your calculation. But if it's not, just recognize that force of friction, if it's going against the motion, most likely it should be negative, or whatever the sign is that lines up with going against the negatives. Because again, in higher level order thinking, we could always inverse our axis, which I tend not to do and I don't want to do, but you could make negative down, positive up. We just don't want to confuse that. So we're going to put whatever the box's direction of movement is, that will be positive, and whatever opposes that motion will be negative, just like the force of friction here. Okay, now let's go on to a third and final example here, and it deals with the following. An object of unknown mass is on an inclined plane set to 40 degrees to the horizontal. What is the acceleration experienced by the object if the coefficient of friction is 0.250? Now, right away, I want you thinking with this one, this is an odd one because they don't really give us a ton of information. You're probably thinking like, we don't have mass. We're just given a random coefficient of friction. Like, how does this help us at all? Well, what we want to highlight here, and I highly recommend you put this in your notes here, is the following. An unknown mass. Right away, I just want you to put a circle with a line through it and say, who cares? Now, this is going to seem a little odd. You're like, what do you mean, who cares? Why would I write who cares there? That doesn't make sense. Like, clearly, we should have to solve for mass at some point. I mean, it's played a role in the other problems, so why wouldn't it make a role in this one? You're going to see why, so be patient with that. The other thing what I'm going to do is indicate the following. The coefficient of friction is this. I'm going to call this mu k. The reason I'm going to call it mu k is because we're going to assume that this object is in motion because it's talking about some sort of acceleration happening. So we could just call it mu and just live with it as mu, or we could put it as mu k where it's mu kinetic, it's in motion, it has some sort of kinetic coefficient. Okay, let's draw out our free body diagram. Again, make your free body diagram a decent size because it really helps identify what forces are at play without crowding them all into a given diagram. So here we go. Here's our box, just like we've had before. And I'm just going to tidy that up a little bit. I always want to make sure I have a neat free body diagram. There we go. Okay, now let's start putting all our forces together on here. So we have our Fn, we have some sort of force of friction, and I'm going to make sure I put these in here. So this is Fn, this is force of friction. Again, you could put force of friction down below where it's opposite of the F parallel. I tend not to do that though because it's a little bit odd. Okay, now I'm going to draw my FG downwards. I'm going to break it into its components. So one component, which is the Y component of FG. We have an X component of FG. Now we just want to make sure we label them all. So here's FG, here's F perpendicular, here is F parallel. Now again, why are they F perpendicular and F parallel? One is perpendicular to the surface, one is parallel to the surface. So that's how we determine it. Okay, and then just as an optional thing, you could write this again as the force of friction down here opposing the motion of the F parallel or opposing the force of F parallel. If you wanted to do that, that would be okay. I just like to draw them all connected to the box rather than drawing them off of other vectors. Okay, now we're not done our diagram yet. The other piece that we need to include here is that this is going to be 40 degrees here. Interior triangle, this is going to be 40 degrees here. The last thing we need is our index. The index is extremely important because you don't want to forget which way is positive, which way is negative. If the direction of the box is going down the incline, we make it positive. If up is negative, that means that it is in the opposite direction to the motion of the box as it slides down the incline. Now, below, what we're going to do is take this diagram and then start writing out our FNet statement, because this will be quite expansive. So I recommend draw your free body up on the top here, and then below, we're going to start the expansion here. Now, let's put together an FNet statement. Here's what we got. FNet is equal to F parallel plus FF, or the force due to friction. Now we're going to expand these out. So FNet can be expanded into mass times acceleration, which is equal to F parallel is the sine ratio. So it's going to be FG sine theta, plus on our formula sheet, we have a special connection between our FF and our FN. The special connection is the following, and I'm just going to write it in square brackets up here. We know from our formula sheet, FF is equal to mu FN. And more importantly, it's the absolute values of these, but I'm just going to simplify it to this. So in our expansion here, we're going to write this as mu Fn. There we go. And just to be more specific, if I know that the force of friction is a negative force, what I want to do is put in a negative here rather than a positive. So I'm going to drop the vector symbols when we go from first line to second line, and I need to make sure that my F parallel is positive. It's going down the incline. So this term was positive. This term, once I drop this vector arrow up here, I must include the negative that is corresponding to the force of friction being in the opposite direction. Now, I'm not satisfied with this yet. What I want to do is I want to underline this part here. Fn, we can do a substitution with this. Mass times acceleration is equal to, and same with here, I'm actually going to underline this piece here. Fg can have a substitution. Fg is equal to mass times gravity, sine theta, minus mu. Rather than writing it as Fn, I can write this as F perpendicular, because I know that Fn and F perpendicular were equal and opposite from each other. Just to see that visually in the diagram, this force is equal to this force in terms of equal and opposite magnitude. So I'm going to plug that in here. Now from here, what we want to do is we're not satisfied with this again. F perpendicular, that's kind of ugly. That doesn't really tell us a lot. So what we're going to do is we're going to write this as mass times acceleration, which is equal to mass times gravity, sine theta, minus mu. And then rather than F perpendicular, I'm going to write this as Fg cos theta, because we know that the F perpendicular is in the cos position. If I scroll back up here, I would look at this and say, well, according to 40, this is the adjacent over the hypotenuse, so I'm going to use the cos ratio. And then again, we're not satisfied with this piece here. This Fg here, just like we did with the previous term or with our F parallel, we want to make sure that this is mass times acceleration, which is equal to mass times gravity sine theta, minus mu mg rather than the Fg cos theta. There we go. Now, here's where we get to that point where I talked about where it's like, who cares about what the mass is? When we scroll up here, remember how we highlighted that and we said, it doesn't matter. Like this unknown mass, typically you'd be like, an unknown mass, I got to solve for this. It has some sort of relevancy. In our case, no, it doesn't. And here's what happens. When you look at this algebraically and mathematically, we would eliminate the masses because this mass is the same for all of these terms. So I can actually divide by mass, which will eliminate the mass from all terms. And what this means mathematically is regardless of what mass I put on this incline, if it has the following conditions of the same coefficient of friction, the same angle, and the same height at which it's being released, then it will always accelerate at the same rate, no matter what mass this is. That's what that means mathematically. So if they ever say an object is accelerating with an unknown mass, just realize that when you do your expansion, it maybe won't matter. And even if they didn't say that it was an unknown mass, they might give you this setup. You need to recognize that if you do this type of expansion where you're going to be considering some sort of force of friction and some sort of F parallel alongside of the F net, most likely your mass will actually end up canceling out, which is actually very nice. Now, here's what we can do to continue this, because we're trying to solve for our acceleration. Acceleration is therefore equal to g sine theta minus mu g cos theta. Now, just like we did in the previous problem, we see that we have a greatest common factor, or a GCF of g. So I'm going to take out the g out front of the brackets and make this sine theta minus mu cos theta. And now what we're going to do is plug in the numbers. Now, if you do this step here, this is purely optional. I'm just going to even put that in here. This is an optional step. You could just plug in the numbers once you get to this line here if you really wanted to, but me being the math person I am, I love when we see a GCF, so I can't help but take that out there. Now, what we're going to do is we're going to put this together and say our acceleration is equal to g, which is a signless g, 9.81 meters per second squared, in brackets on the outside, multiplied by sine, 40 degrees, minus the mu, which is 0.25, and then multiplied by the cos of 40. There we go. Close that bracket there to wrap that all up there. Now, therefore, the acceleration of this problem is equal to, and you should get a magnitude of positive 4.43. This will be meters per second squared, which can also be written as 4.43 meters per second squared. And we're going to consider this to be down the incline because remember, positive represents down. So I'm going to say down the inc. There we go. Perfect. There's our solution. So given these conditions, if I zoom out here, and I'm just going to zoom out to the macro level of this problem here, I would look at this and say, at the end of the day, regardless of what mass I put on this incline, as long as it follows that it is sliding down an incline with a 40-degree angle and a coefficient of friction of 0.250, it will accelerate at 4.43 meters per second squared down the incline. Very, very big key connection there. Now, in your notes, here's a connection I want you to write down, and I highly recommend you write this down before we finish off this lesson here. Off in the margin, because you're going to see this connection so many times moving forward, especially in your practice problems and potentially even in the next lesson, let's just make sure we establish that connection right here, right now. Your FF, or the force due to friction, is equal to mu Fn. Now, I'm not satisfied with Fn. I'm going to make a substitution where I say, rather than writing it as Fn, it's going to be mu F perpendicular. Now, instead of writing it as mu perpendicular, I'm going to write this as mu times Fg cos theta. Which, again, I'm not satisfied with Fg. This force can be transformed into being the following, and I'm just going to make sure I put it in green here. This is equal to mu, and then this is going to be mg cos theta. Okay, and then because force of friction is a negative force or an opposing force, what you can do here is you can actually write it as the following, where we can write these as the following, like this. Once I go from my Fn to my F parallel or my F perpendicular, I can put a negative, I can put a negative, and I can put a negative, because we know that Fg as a force is negative, F perpendicular is negative as a force, Fn is a positive force, but by definition on that first one here, we don't really need to do anything with it because we still have our vector symbols above, so we have an assigned sign. Once you drop that vector symbol and you go into the below forces, that's what you need. And what I would do is I would box, highlight, or star this, and I'm going to just use a different line here. Maybe I'll use black just to box this in here. So I would highly recommend you write this in your notes somewhere in the margin just to make sure that you have this for yourself, because as you're doing your practice problems, you're going to want to get comfortable with that substitution, going from one force to the next, creating that connection of how they go from one to the other and how they are equal in magnitude, but maybe opposite in overall sign and direction.